Hello, 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 everybody. Welcome to Science. Here we are, we're behind the desk today, but we have a lot to do. So let's take a look at it. Today, we're exploring the relationship between the sun and your shadow. You're gonna need your science notebook, something to write with, to take notes. It is gonna be important here. And then we have a lot of I cans today. Some of them are leftovers from last time that we'll quickly review, and then we'll get back into it. I can define shadow in a scientific context. I can observe how outdoor shadows change throughout the day. And I can use an if-then sentence to describe the cause and effect of the sun's position on shadows. So last time we talked about a lot of things. We talked about this idea that shadow is really the absence of light because it's being blocked by some solid matter that is not transparent or translucent. Light can't get through it. So those beams of light hit whatever solid object there is, and then there is less light behind it, creating a shadow. So you need a light source to have a shadow, right? In a dark room, you're not going to have a shadow. They're not going to exist. You need light to have a shadow. On a cloudy day, you probably won't see a shadow on the ground because it's just not bright enough to have a shadow. Right? That was the trouble last week when we were supposed to do this lesson, but we had a big rainstorm and it was cloudy all day. And how can we get data on our shadow when there are no shadows to be had? There we are. Let's think about what else we know about the sun and our shadows. We know that the sun is not in the sky 24 hours a day, right? The sun, well, we made a good point last time because I talked about the sun moving across the sky, but I'm going to use the term perceived movement because the sun itself, as many of you smart cookies pointed out, the sun itself is not doing the moving. Okay, the sun is at the center of our solar system and we are moving around it rather than the other way around. And because the Earth is rotating on its axis and turning, we perceive the sun as to be moving across the sky because we are in fact turning around. And when it's nighttime, we're not facing the sun. When it's daytime, we are facing the sun, right? The sun seems to rise from the horizon and then set back down at the horizon. Okay, so it's in kind of making this arc, right? It starts with a rise in the east, comes up, and then goes back down in the west. Okay, so these are all important things to think about as we think about this investigation. So let's get into it. Here's Gene. There he is, right there. Hello, there's Gene. And Gene was our test subject for this as we were mapping out our different intervals and our different shadows throughout the day. So essentially this investigation was, we're going to, at regular intervals, every hour, take a shadow reading and take a shadow outline like we did in Investigation 1. And attempt to get more of a systematic and more of a clear idea of the relationship between the sun and the shadow. Because we took 2 shadow measurements last time and saw that they were in very different places. But we want to go further. We want to know how those differences are. So there's Gene out there. Everyone wave hello to Gene. And we took some measurements. So we started, the first one, this is from our first investigation, but for this one we started at 9 a.m. There is a shadow at 9 a.m. Okay, and as you can see, I'm standing in the middle of it. It's pretty long, right? Now let's think about what's happening in the morning, right? The sun's just starting to come up. It's pretty low in the sky. We've got a really long shadow, okay? And here is our 9 a.m. shadow. And as you can see, the sun is pretty low in the sky, right? It's just above the buildings here at Glenview. Okay, so there's the shadow there. Let's jump ahead. Okay, now we have our 10 a.m. shadow. And as you can see, I'm standing right at the point where Gene was. And as you can see, the very tip of Gene's witch hat there, a lot shorter of a shadow after an hour has passed. So we see 9 a.m., we see 10 a.m. We're going to look at these exact numbers in a little bit, but a little photo collage here at the start. Okay, so there's that. Next, we have, whoops, I moved the wrong one. There we go. Next, ta-da, there's Gene again. And this is Gene in the middle of the day. We've taken a whole lot more measurements. As you can see, there's our 9 and our 10 a.m. Shadows on the left. And what happened was, as you can see, there's kind of all over the place. Because it was a partly cloudy day, I couldn't get readings at 11 o'clock or 12 o'clock yesterday. I had to run out and get them today. So this is from this morning at 10 a.m. when I'm taking the 10 a.m. shadow. And as you can see, very, very, a lot shorter. Again, you can see Gene's shadow in that 10 a.m. mark there. Okay, and then to his left, our right, we see there's also some other ones I took from the previous afternoon. Let's jump ahead here. Next. Ta-da. Oh, is that the same picture? It is the same picture. Okay, let's jump ahead one more. There we go. And as you can see here, we have, starting from the left, we have 9 a.m., 10 a.m., 11 a.m., 12 a.m., and 1 p.m. So we have 5 different measurements, 5 different shadows, 1 each hour. And as you can see, take a look at the tops of Gene's witch hat on all 5 of these shadows. Do you notice how it makes kind of a, almost like a very subtle curve, or almost close to a straight line, right? That's telling us that the sun is moving at pretty regular intervals, right? This is why we did it once an hour, right? If the sun was like, if the rotation of the earth was like speeding up and slowing down, it might look a lot different, but the earth is rotating at a nice steady rate, and so we're getting a nice steady shadow. And then the last one I just want to point out, look here. This is at 1 p.m. As you can see, there's Gene's shadow, and then there's the 1 p.m. mark right there, right in front of us. Check out where the sun is. You can't even see the sun because it's all the way up above the photo, right? Let's compare that to, I believe it was this one. Oh, nope, not that one. It was this one. Let's compare that to this image at 9 a.m. You see how low the sun is in the sky? By 1 p.m., the sun has gotten so high in the sky that we can't even see it anymore in this photograph. It's up above the photo. So a higher sun and a shorter shadow. So there's our if-then sentence right there, right? If the sun is high in the sky, our shadow will be short. Because again, it's all about angles, right? If I have a high, come over here, if I have a high shadow over here, and here's my thing, right? As the light beams come down, they're hitting at a steeper angle, a more acute angle to the object, and so there's going to be less space for that shadow to be. Whereas here, if it comes in this way, that's a lot of light hitting all of these points on our object, so our shadow is going to be really long and really big. Okay? Let's take a look at our data. So here's the number data. So we notice at 9 o'clock in the morning, we had a 584 centimeter shadow. 584 centimeter shadow. If you want to do it in meters, you divide by 100, so 5 and 84 hundredths, right? 5 meters, almost 6 meters, that's like, you know, if we're converting that to feet, that's somewhere in the range of like 18 or so feet. It's a really, really long shadow from Gene, who's about a little less than 6 feet tall, right? So about 3 times his height is that shadow. And then we see here, 10 o'clock, it goes down to 324 centimeters. 11 o'clock goes to 225. 12 o'clock goes down to 179. 1 o'clock goes all the way down to 168. Now, I had this thought. I was like, well, I'm noticing it's getting smaller as we go throughout the day. So does it just keep getting shorter and shorter and shorter until it disappears at sunset? So what I did, I didn't get a chance to get 2 o'clock or 3 o'clock readings yesterday because it was cloudy, but I did get one at 4 o'clock, and you'll notice at 4 o'clock, it goes back up to 245 centimeters. So it's getting longer now that we're in the late afternoon. And that makes sense with the position in the sky, right? The sun is starting to go down. It's starting to get closer to sunset. So lower in the sky means our shadows are getting longer and longer again. Now, I put these on a couple of graphs here that I want to show you, because if we go back to this last picture of our 5 shadows here, it's a little hard to see, right? We see 5 shadows, they're all lined up, they're all short, but it's really kind of hard to see the correlation, particularly because there isn't like a northeast, south, and west in here. So what I did is I went ahead and I graphed it. And it looks like this. So as we can see here, up at the top of our graph, there's north. Okay, I used my compass app on my phone. You can use an actual compass. And I found north, and I marked it on the ground. And then south at the opposite, west and east. And then I went ahead and I used the lengths of the measurements that I took and put them kind of on a graph. So those little dots at the end, at all the times, those are the tops of Jean's witch hat. And as you can see, we can kind of picture our sun moving across the sky a little bit from left to right. We kind of get, if we were to connect all these dots here, I'm going to connect them in pink here. If we were to connect all these dots, so here's the tip of his hat, right? It kind of makes a shape like that. So if we were to continue to follow it, it stands to reason that maybe if we took one at like 6 or 7 o'clock, it would end up over here, right? I also put this in another graph in another way because I wanted to see kind of this information here just on height. So this one looks like this. On our horizontal axis, our x-axis, I've got the length of our shadow in meters, okay? And then on the y-axis, the vertical axis, I've got the time of day. So I've got 9 a.m. up there, down there at the bottom. And then I've got, you know, going up and up and up and up and up, and then 4 p.m. is all the way at the top. And as you can see, it kind of makes, I'm going to do it in pink again. If I were to connect these dots, I'll use the ruler to connect these dots here. If I were to connect these dots, it's kind of making a little bit of a similar curve to what we saw on our other shadow chart. Except this time, because I oriented it in a different direction, we're kind of moving in a different place here, right? So this allows us to see, you know, if I were to go out, and I think I will because I have the time this afternoon, if I were to go out and it's a nice sunny day, and take measurements at 2 o'clock and at 3 o'clock, I can predict, based on this data, that the lengths of these shadows are going to be somewhere in this region of space. So somewhere around 2 meters. And I'm going to confirm that when I go ahead and look at our data this afternoon, right? Just like our other graph here, I could also predict that the end of Jean's witch hat at 2 and at 3 are probably going to be somewhere right in here, following this line across. Okay, so that's the beauty of data. Pretty cool stuff. So, to sum up, as we're looking at a lot of this data, what this proves, as we look at, let me go back to our graphic organizer here. As we look at our data and we see the closer we get to the middle of the day when the sun is higher in the sky, the shorter our shadow is. The closer we get to the ends of the day when the sun is low in the sky, the shadow is longer. So we can make an if-then or a cause and effect statement off of that. If the sun is high in the sky, then our shadows will be short. If the sun is low in the sky, then our shadows will be long. You can also do it the opposite way, right, to kind of prove it. If we observe a short shadow, then the sun must be high in the sky. If we look at our shadow and it's a really long shadow, then the sun must be low in the sky. Okay? On our exit ticket, you're going to be answering a few of these questions, like where's the longest and the shortest, what time were the longest and the shortest shadows. So make sure to look at this data right now. What time has the longest shadow? What time has the shortest shadow? Just leaving it up there for you. How nice am I? You could also look at our graph for that information as well, right? Where's the longest shadow? Which time of day is furthest to the right, because our horizontal axis is getting bigger as it goes to the right. And which data point is furthest to the left? All right. So, and then after that, we're going to be doing some if-then statements about the relationship between the sun and our shadow. All right. If you wanted to try this at home, you certainly could. Again, you'll need a partner. You'll need probably an alarm clock to remind you to go outside and take a chalk measurement every hour. And you'll probably need some paper and a measuring tape to collect some data. All right. Cheers. Good luck. Thank you for tuning in. Do that exit ticket and have a great rest of the day. And I will see you soon.